extremely expensive process, and it's a very complicated process. So this is an expensive lab inside which the transistors are fabricated. Okay? And the picture that on the right bottom that you see, it's a black and white image. It's called an electron microscope image. Okay, electron microscope image will zoom at a very large scale, so you can see the scale that mentions here 200 nanometer, which means this line that you see the scale is 200 nanometer. Can you imagine how small 200 nanometer is? For example, if I tell you 1 centimeter or 5 centimeter, what will be 1 centimeter? You know, like the size of your nail maybe, or 10 centimeter, the size of a small scale or a ruler. So can you have a feel for what 200 nanometer is? It is very, very, very small. We cannot see with our naked eye. Okay. Is my voice audible and visible? Because I hear absolute silence, so I'm not sure if audience is able to hear or see me.
Yes, yes.
Okay. Thank you. Yeah. So I welcome questions in between. Okay. Please feel free to stop me anytime or ask questions directly on the microphone. It's okay. Okay. You can raise hand. The moderators are there to help moderate, so not an issue. So this is 200 nanometer. It's an extremely small dimension that we cannot see with our naked eye. Do you know why we cannot see with our naked eye, by the way? Because we see only those things where, because we see it with a visible wavelength, right? We only are sensitive to visible wavelength of the electromagnetic spectrum. And 200 nanometer is smaller than the visible spectrum of the colors. So we cannot see this dimension. This is too small. So now we need to get a feel for how small this dimension is, this 200 nanometer dimension is. Okay. Just hold on for, I'll just change my seating arrangement. Show you my hassle. Alright. So I'll show you how small this device is, okay? I'll show you. So now this is an image. You can see that's a long thread-like thing, that is human hair. There is a single human hair. Okay, one strand of hair, it is about 50 to 180 micron, and 1 micron is 1000 nanometer. So you see the human hair is 50,000 nanometer. So how much will be 100 nanometer? How small will be 100 nanometer? So some sizes are given here. This is a sand particle, this is a salt particle, this is a white blood cell, this is a red blood cell, right? This is a dust particle, this is a bacteria, this is coronavirus. You see, every year we have coronavirus now. So that, my pointer is here. That is coronavirus, that is around 100 to 500 nanometer. Okay? Smallest is Zika virus. Zika virus is 45 nanometer. We cannot see this with eye. This is a magnified scale compared to the human hair. Okay? So the transistor I am talking about is here. It's smaller than probably the coronavirus. The channel, this particular channel is less than 100 nanometer. It's smaller than the coronavirus. Okay? It's that kind of small device that we have in today's world. So now that I told you that transistor is the link that connects the three, pictures. Question is, how many transistors are there inside a cell phone? Okay, how many transistors are? Here. Why is the video not running? Just give me a second. I'll just make sure the video runs, because hope the video will run now. Okay. So I'm showing a video, and these are all available in the public domain. So this is not what I'm doing. I mean, this is not my original video. I don't own copyright. This is available in the YouTube. I'm just showing it here. This video is of probably around 2 minutes. It will zoom on an electronic chip. So you see, this is an electronic chip that you can find if you open your cell phone. Okay, a picture on the top, it shows, the back side of the cell phone. If you open up and you disassemble, then you will find these electronic chips there. No, so this is one of the chips that is there. Okay, the back side of the cell phone. Now, if you zoom, if you keep enlarging and magnifying the image, okay, and eventually we have to take help from electron microscope, because visible wavelengths cannot help us see these tiny images. You will see, okay, those are tiny structures that are coming in here. It's going below. Now you see there are some lines. Okay, and you see the lines are so neatly arranged. They are so precisely arranged. All the structures below are laid down with such precision, without any error. Look how beautifully this is done. This is the technique to make this is called microfabrication or nanofabrication now, because they are almost approaching nanometer. Okay? The precision with which they are done, you cannot have error even in the range of 100 nanometer. If your movement of this line has an error of 100 nanometer, you will short the circuit. These are tiny lines of 1000 nanometer. Okay, and modern technology is even beyond that. This is probably a few years old, maybe 10 years old. Okay, so this essentially gives an idea that there are so many transistors or so many nanostructures inside the cell phone chip. Okay, there are millions and millions of them inside. Okay, in 1970s or 60s, we only had few hundreds. Then the number increased 1,000, 10,000, lakhs and tens of lakhs, crores. Now we have crores of these devices in each cell phone that enables the device. And how do we know? And the reason they are actually, the reason that they are squeezing, there's so many millions of them inside, is the reason why our laptops and cell phones are becoming superior with every year. They are becoming faster. They can do so many other things. A cell phone can do so many things. Internet, camera, video, and so. So 10, 15 years back, many of the functionalities are not there. So every year, every 2-3 years, we see the cell phones with new functionalities are coming out. Okay, new camera, enable new faster devices. So many new added features are coming out. How is this possible? This is not magic. This is the number of transistors. Okay, in the circuit is going up for the same area. The same area, you are having more and more transistors. Okay, so there's a beautiful thing that's happening actually in the ground floor. Okay, that's what it is. So that integration of millions and billions of transistors, this is what it makes IC. It's called integrated circuit. Okay? The integrated circuit technology is what has revolutionized the modern technological world. Okay? 2000, in year 2000, the Nobel Prize was awarded to these 3 gentlemen. 2 of them, okay, the first one and the last one, these 2 gentlemen actually invented and innovated this integrated chip technology that has made modern life possible. Person in the middle, Herbert Kromer, is another person who invented the laser. I'm not going to talk about that right now, but we use that device every time because all the data that we have comes through optical fibers. The optical communication, you need these semiconductor diode lasers to actually modulate the signal. Those are very vast topics that it will need 1 semester course actually to cover. So I'll not talk about all these things. I'll just briefly go through the basics of transistors only. Okay. Now there are many fascinating things about transistor. I showed you the basic fabrication thing and the basic idea, but there are many things that we will see. Okay. So this plot, you see this plot? This is a famous law. It's called Moore's law. Okay. Those of you who are probably doing PhD or who are doing masters will probably have heard of this law called Moore's law amongst those who are doing BSc. And here it is your chance. Moore's law essentially tells that the number of transistors, okay, please remember the number of transistors in a given area of the chip module, it becomes almost double every 1.5 years. Okay, it's not a limit moving, but it's how the integrated circuit technology is evolving. Okay, so on the y-axis we are showing the transistor number, and on the x-axis we are showing the year starting from 1970 to 2016. So it's a image rising. This is rising logarithmically actually. So every 1.5 years the number is doubling. Okay. So you can see that at 2016, this computer has 8 core, for example, i7 core was there. So the number of transistors was 1 billion. Okay, the number of transistors was 1 billion inside a core i7 processor. Can you imagine the number of 1 billion transistors inside your laptop or inside your mobile phone? That's insane. That's crazy, right? So it's going on increasing, and there will be a limit eventually because there is an atomic limit. So people are trying. A lot of innovative and scientific research is being going on to see how we can pack more and more transistors today, because we are approaching the atomic limit. We are approaching the limit of 1 atomic layer very soon. You cannot go below 1 atomic layer, right? So these are very, very exotic things. There's a lot of material science, physics, chemistry, maths, many things are involved. It's all multidisciplinary research nowadays. Okay, and this enables and this translates into the modern cell phones, modern gadgets, wearable phones that are coming up. All these are happening because of this fundamental, research that is taking place. I have to mention here that transistor research is not the only research. There are also other many things in the computer architecture, in the memory, the way memories are designed, the programming languages, the many things. I'm just talking about the transistor, which is the device that enables all this. Okay. So now, this is an interesting analogy I will show you. I'll tell you. So if you talk about an automotive vehicle or just car or something, so the x-axis is performance and the y-axis is cost. If you want to buy a bike or a car, the cost is proportional to performance. You know, so an Indian auto will probably be one auto. If you buy a Maruti 800, the cost will be a little better, more, the performance also will be better. If you buy a Honda, maybe City or a Honda Accord, cost is also much higher. Performance is much better than BMW. Ferrari is $10 million. The racing cars, the performance is the top of the world. So this is how it is. You pay more price, you get better performance, whether it is car, scooter, or even any other food items. If you buy expensive, you generally have a better quality. But this trend is actually exactly opposite in semiconductor. With higher complexities and better performances, the cost is actually coming down. Let me give you an example. I bought my first laptop in 2004. Okay, that had a RAM size of I think 128 MB. Okay, a RAM of 128 MB is laughable now. You cannot get computers with RAM of 128 MB. So my laptop was IBM. It was 128 MB, and the memory was I think like some 256 MB. Okay, hard drive, and the laptop cost me 60,000 rupees. Today is 2020, 16 years from then. Today, at 60,000 rupees, you can get a Dell Inspiron laptop that is infinitely faster and better than that IBM of 2004. You do not get 128 MB RAM, you get probably 16 GB, 32 GB RAM, okay, and 500 GB or 1 terabyte of solid state memory, not even magnetic drive memory, and it's super duper fast, right? What does it mean? For the same price, okay, in fact, I'm not even adjusting for inflation. Okay, 60,000 in 2004 is probably 80 or 90,000 today. I don't know, something like that. So, for the same price, you are actually getting a much better performance, 100 times better performance. What does it mean? For the same performance, the cost is coming down actually, right? So that is the beauty of semiconductor industry. That is because the cost of the transistor, each transistor, is coming down ridiculously low. So the figure on the left here, the y-axis is the cost per transistor, and the x-axis is the size of the transistor. So as I'm going from left to right, the size of the transistor is reducing. So you see, as the size of the transistor is reducing, the cost per transistor is coming down. Why? Because in the same chip, when you had 1,000 transistors, now you have 1 million transistors, but the price is remaining the same. Okay, so that means cost per transistor has come down by at least 1,000 times. Okay, the right figure here actually shows the speed, how fast the device can work. You know, it relates to how fast your computer can boot up and things like that. So the speed is becoming more and more shown by this arrow as you're actually reducing the size of the transistor and you are reducing the leakage. There's something called leakage. Let me not talk about that right now. So no other technology in human civilization offers this advantage that for the same price, the performance actually becomes better over time. Okay? So if this scaling continued in automobile industry, then today a Mercedes-Benz should have cost us less than 1 paisa. This is that kind of scaling that is happening. This is called scaling the transistor, okay? You can see it, of course, right? You can see it. For the same price, every year, you actually can get better cell phone. You know, in 2014 or 15, the kind of cell phone that you got, and today, the kind of cell phone that you get at similar price, so much, this entire thing is at the heart of that, okay? This entire thing is at the heart of that, okay? If there are questions, please stop me, okay? Because it is better to ask and interact than to not ask at all, okay? And as I told you, you can ask questions in Assamese also. Please feel free to do that. So now I have spoken so much things about transistor, you know, how fabrication is done in some aspect, and you know what I do. Question is, what are actually transistors going to do? How do they work? Okay? So, you know, I'm showing you the back side of a cell phone. Sorry, I'll just drink water. So this is the inside of a cell phone. There are so many chips. You see, there is a chip called microprocessor and control logic. You know, our technology is digital. You have all zeros, ones, right? Those are digital technology. So microprocessor and control logic actually is the heart of it. You know, this will all need an engineering semester, but I'll just tell you generally that microprocessor is the processor that controls all the functions. You have all the digital logic like NAND, AND gates, NOR gates. Everything is happening there that enables the functionalities. A chip over here is RF transmitter and receiver. Phone does not magically send you the picture or video. It has to convert the signals, the zeros and ones, into electromagnetic waves, probably around 1 gigahertz or 2 gigahertz. And it has to send these waves through an antenna to the atmosphere, okay, to the nearest base station. So the radio frequency transmitter and receiver is for that. And this transmitter receiver is typically made of, you know, complicated devices, transistors, but a little bit more advanced transistors. Okay, I'll talk later. And then there's power handling module, there's memory. You have to store the data, so there's memory, there's audio, video, there's so many components. So transistors are in most of these components. Okay, millions of transistors are in most of these. So that's what transistors do. Now I'll define the transistor more formally, okay? And this is very high school physics. If you take 2 points A and B on transistors in most of these components, okay, millions of transistors are in most of these. So that's what transistors do. Now I'll define the transistor more formally, okay? And this is very high school physics. If you take 2 points A and B on a material, okay, if you take any material, suppose you take a piece of iron or a piece of copper, metal, for example, the current that flows between point A and B will depend on the voltage that you are applying between A and B, right? If you apply 1 volt, some current will flow. If you apply 10 volt, some more higher current will flow. A transistor is a unique device in which the current flowing between A and B does not depend so much on the voltage difference between A and B, but on a voltage that you are applying or a current that you are supplying at a third terminal, C. Okay, so you are able to control the current in a material by controlling the voltage or current on a third control. This is a very beautiful concept. It's like a water flowing in a tap. Okay, the water is flowing here, and then you have a tap with which you can actually control the flow of the water. Suppose the tap, this water pipe is slanting, and there's a reservoir of water fitted at one side. So because of the slanting line, water will continuously flow. But now if you have a tap, you can actually control the flow with the tap. Although there is a slope in the water line, you can still control the flow with the tap. So the water flow is happening between 2 points. The current flow is happening between 2 points. We call them source and drain. Typically, okay, source and drain. That is where the current is flowing, and you are controlling that with a third terminal called the gate. Okay, that's called transistor gate. Now this is an image. Again, I'm taking from internet. This is an image of a transistor. You see, this is a source. This is a drain, and between them there is a material. It's called semiconductor. Okay, it's called semiconductor. There are many types of semiconductor. The most common type of semiconductor is silicon. Here I am showing a semiconductor, different semiconductor called MOS2. Don't worry about that at all. So this is a semiconductor between source and drain, and there is a gate. So the current flowing between source and drain will depend on the voltage that you are applying on the gate. That is the beauty of the transistor. That's how it is used as a switch. Matlab, you can apply voltage on the top gate, and you can ensure that either current flows or current does not flow. So it's like a switch. Either it is on, current is flowing, or it is off, the current is not flowing. And for that, you don't have to depend on the 2 terminals, you use the third terminal. So that's a very beautiful concept, right? So transistors handle these zeros and ones in a digital circuit. Okay, zeros and ones in reality are actually the amplitude or frequencies of electromagnetic waves. Okay, and the way you receive and transmit them from a cell phone, where you process them inside a cell phone. If you suppose you are sending a selfie in your Instagram profile, the selfie in the Instagram actually is combination of many zeros and ones. Means there are many electromagnetic signals whose amplitudes are changing to manifest as zeros and ones. Okay, so the transistor is again processing all these zeros and ones. Transistor is sending these zeros and ones. Transistor is also receiving these ones and zeros. Okay, so that's how is happening, and the basis of this is a logic gate. Okay, so these are 2 different transistors. You see the red circle I'm putting here. Let's not worry about the details of the technicalities here. There are 2 transistors here. I'm using the 2 transistors to essentially, there's a is input, and then there's a Q, that is output. So you can give a 0 or 1 as an input, and you can have a 0 or 1 as an output. So that enables a logic operation. And when you have billions of transistors, you have these billions of zeros and ones to have the logic. That eventually gives you the processor. This is a Qualcomm processor that goes in your cell phone, for example. This is an Intel processor, older generation, that used to go into desktop or cell phones. So these processors enable your digital logic. Okay, and this kind of complementary logic gates, we call them logic gates, are actually mirrors that go inside this. Okay. Now, what is the material used for transistor? I told you rubber, glass, wood, diamond, etc. The main difference between metals and insulators is that metals will always carry electricity when you apply voltage, and insulators can never carry electricity. And there are insulators that are like rubber, glass, wood, diamond, etc. The main difference between metals and insulators is that metals will always carry electricity when you apply voltage, and insulators can never carry electricity when you apply voltage. For example, if I take a piece of rubber or piece of oil or something, bucket of oil, if I apply a voltage, then I get negligible current. The current almost doesn't exist. It is almost zero. If you take a piece of gold or copper or iron, you cannot make it non-conductor of electricity. What I mean is that across a piece of gold or silver, if you apply voltage, it will always carry current. You can never make it not carry current. Okay. Similarly, across a piece of glass or rubber, it will always have no current. You cannot make it carry current. Okay, that is the property. Semiconductors are beautiful substances. The reason I call them beautiful is because you can tune the conductivity. I mean, you can change the conductivity. Semiconductor wafers can carry current almost as high as metal. At the same time, you can make them almost as insulating as a piece of rubber or glass. Isn't it beautiful? The same material, it can carry very high current in certain conditions, and it can carry no current under certain conditions. That is how you make a switch, and that is how you make a transistor. So that's a very beautiful property of semiconductor. Example, silicon. So figures that you see here are silicon wafers. Semiconductors exist, we buy them, not exist, sorry, we make them or we process them in the form of wafers. So you see these wafers, there are different sizes. The diameter can be 2 inch, 4 inch, even up to 12 inch or 16 inch. These are thin substrates, we call them substrates, on which device fabrication is done. When I say device fabrication, I mean fabricating or manufacturing hundreds, thousands or millions or billions of transistors. That is called fabrication. Micro fabrication or nano fabrication. This micro or nano fabrication is done on the silicon wafers or semiconductor wafers. Okay? How thick is this wafer? This can be around 200 to 2000 micrometer thick. To give you an idea, 2000 micrometer is 2 millimeter. So you know how 2 millimeter is, right? So 200 micron is essentially 1/5 of 1 millimeter. Okay, you take a plastic ruler that you have in your school. That ruler, the smallest gap is 1 millimeter. You know that, right? So you imagine that we divide that gap into 5 equal parts. So that small one part is 200 micron. So the thickness of this wafer is typically 200 micron. And the dimension I told you, the diameter of this is probably 2 inch, 4 inch, 8 inch. It can be different sizes up to around 16 inch. Okay, and they're very, very shiny because they're polished in an atomically thin or sharp way. Okay, so these are semiconductor wafers on which fabrications are done. Now you see this. This is a dust particle. This dust particle is very tiny, but guess what? The semiconductor devices that you have are also tinier. So what it means is that when you do transistor fabrication, those hundreds or thousands or millions of transistors for your cell phone, when you do, if a dust particle comes and sits like this on your device, on your transistor, and the transistor is similar in size or smaller in size than the dust particle, then what will happen? Dust particle may short two devices, or it may damage the two devices. It will lead to malfunctioning of the devices. And if devices malfunction, then your cell phone will not work, right? It will have noise, it will have all kinds of bizarre problems, strange things coming up. What it means is that you cannot afford to have any dust particle come inside the fabrication lab. Okay, and you know what? There are millions of dust particles in the air. Every time I blink my eye, I close my eye and open the eye, the skin in my eyelashes and my eyelids, the skin will shed about 1000 dust particles, for example. Every time I move my hand like this, my dead skin will come out, will give out around 1000 dust particles. We cannot see them, they are very tiny. But those 1000 dust particles will go and sit and they will damage 1000 transistors. And then that's it, your circuit is gone, right? What it means is that we cannot afford to have any dust particle in the fabrication lab where transistors are being made. Okay. So this is a special lab, it's called clean room. And the clean room need not be all yellow. The yellow is on this portion is white. This one portion is called gold room inside the clean room, not because there is gold here, but yellow light is used because there is a special chemical substance that has to be used to fabricate these transistors. That substance is sensitive to photons of higher energy. For example, in a visible light, in a surrounding sunlight or tube light or bulb, you have light of also higher energy, like blue component that you cannot see, of course. That will damage those chemicals. That's why you should use a lower wavelength light. Now, red is the lowest wavelength light. Okay, so ideally you should use a color room whose background lighting is red. But then alarms are also red. If there's a fire or some kind of problem is happening, then the alarms have to blink, blink. So the red color has to blink. So yellow is the best light that you can have, such that the material is not sensitive. Okay. And this room is extremely clean. That's why it's called clean. How clean is this? This room is about 1000 to 10,000 times cleaner than this room. There is a special airflow that will happen. It will ensure that you have minimum dust particles. There are different categories of this clean room. Clean room of plus 1000, plus 100, plus 10, like that. And that number essentially indicates the number of dust particles of a particular size that you have in a unit volume of the room. Okay, so that's very highly controlled. It's very expensive to build. You need crores of rupees. This kind of facility that Intel has, for example, some 60,000 crore rupees to make. Okay, that's a huge investment. Okay, and inside the lab, you have to wear this kind of suit. You also have to wear a mask. This person has not put on the mask yet. This looks like a COVID healthcare worker suit, but this is called a clean room suit. This is not a COVID suit. It probably can work for COVID, I don't know. Okay, but this is a suit in clean room to prevent dust particles from your dress, like shirt or salwar, whatever you're wearing, and from your face also. You have to wear a face mask. It prevents the dust particles and skin particles from your body from coming off and contaminating the room. Okay, that's why they are using this. Now, there's a video here. I'll skip this video in the interest of time. I have a better video in the next slide. Okay, I'll show you. This is a video from Intel. I'll show you how. There's a sound also here. The video will tell you how devices are made. Millions of transistors are made in Intel. Remember, these are made on silicon wafers, semiconductor silicon, and silicon is used because silicon is very good semiconductor. It is most abundantly available. Why do you know? Because silicon is made from sand, and sand is everywhere on the earth. Okay? The video is essentially from sand to silicon. Okay, you'll see that. Video is probably around 2 minutes. You please bear with me. Okay? I don't know why the video is okay. Let me try again. Yeah. So this is your sand. You have to purify the sand first, and then you have to make a very high temperature. You make this thing called ingot, like a block of silicon. Then you dice it. You make these wafers. Okay. I hope there is no lag in the video. This is the wafer. The wafer has to be polished atomically sharp. Okay, these are very expensive processes, by the way. Then there is something called photolithography. You can imagine this is like the old school photography technique. You have a mask and you are shining light. The pattern of the mask is transferred on the wafer, and then you inspect the wafer. Now you do something called doping. This is to increase the conductivity of the material, to make it conductive. Okay, this is how it looks. One particular area of the silicon wafer. Now you see how the fabrication is done. These are all done by machines, human operated or even automated. These are processes called metal deposition, processes called etching. These are very involved processes. I cannot explain in one lecture, but this is how fabrication is being done. Okay? These are layers of metals that are put, for example, etching done to get a structure like this. Okay? There are machines for doing this, lithography and all. Very expensive process, very complicated process. Very highly skilled training is needed for doing this. Okay? Then you evaporate copper, for example. You do electrolysis. You make the metal plate, because there are so many complicated steps to making a transistor. Okay, and then you polish them, you make them planarized. Then you have these many transistors that are formed, and then you connect them together with different connections. These are called interconnects. And then you have those millions and millions of those transistors, transistors in one chip. A billion is 100 crore. Okay, that's how the wafer looks like. And then this is dicing the wafer. Dicing means cutting the wafer precisely. Okay, it has those 1 million transistors per, and they put it in a chip, and that goes into your cell phone, into your laptop, and so on. Okay, that's how your chip manufacturing is done. I had shown it in probably 1 or 2 minute video, but it's a 60,000 crore rupees expensive process that needs 50 years of expertise to do it, of thousands of tens of thousands of expert people. Okay, very complicated process. That's how we get everything. We see this miracle called internet and the integrated technology revolution. Okay, the transistor is at the heart of all this. Okay? Now you might still ask, how did they make these 1 billion transistors so precisely? You remember that mask I was talking about, the shine, light, and then project, the photolithography. In the mask, actually, you can have billions of transistor patterns that you shine, light, and project on a wafer. Then that's how you proceed doing that. Okay, so that's a process called photolithography. Okay, you imprint, you transfer the imprint from one layer to another layer. What am I doing on time? 3:45. Probably I started 5-10 minutes late, so still have some time. Dr. Roy, I have some time, no? Dr. Ramkishore Roy, am I audible?
Yes, sir.
I have some time, no? I have 15 minutes, I guess.
Yes, we have a lot of time.
Okay. So, I'll wrap up in this. So, if transistors are people, then the scaling of these numbers is actually a miracle. So, 1970, imagine the number of transistors was equal to the number of people who can sit in a musical hall. And in 2011, the number of transistors is equivalent to the number of population of China in the same area. So that kind of increase from 2000 devices to 1 billion devices in the same area has happened over last 40-50 years. This is called Moore's law. This is scaling of transistors. But all that I have talked about till now is mostly about transistors for processor or logic gates. But there are transistors that are applied for different other applications also. Okay, for example, look at a cell phone or a laptop. You're charging it. The plug point that you're connecting your charging point, it's the plug point that you have in your house is 220 volt AC, but the laptop needs 20 volt DC. The mobile phone needs around 5 volt DC. You are converting 220 volt AC to 20 volt DC. So there has to be something called a power converter. It's a power converter. You're converting AC to DC and also you're decreasing the voltage, stepping down. So this happens also through a circuit called a converter. Okay, and that converter also needs transistors to do this. It's called SMPS, switch mode power supply. Okay, so you essentially need a transistor that can switch to convert AC to DC and convert the voltage. So transistors are not only used in cell phones and laptops for processor, but transistors are also used in converting electricity from one DC form to another AC form and so on. This is called power converter. The power converters are not very efficient. That's why your laptop adapter is a little warm. The cell phone also becomes warm. That is the waste heat that is dissipated. And now as the number of people, the number of transistors, cell phones, laptops is increasing, that waste heat needs to be minimized. Otherwise a lot of energy is wasted in the whole world. So people are looking for newer kind of transistors, newer kind of materials beyond silicon to make these transistors that are more efficient. Okay, I may talk about that a little later. One of this electricity conversion is in charging your electric vehicle. Actually, the number of electric vehicles is increasing very fast. In the Western world, it is already very large. In Bangalore, Delhi also, the number of electric vehicles is increasing a lot. You have these charging points in the airport, in the road. So this charging of the electric vehicle also needs transistors to convert the power. See? So transistors are everywhere actually. Okay. And always remember that as a country becomes more and more developed, the fraction of the total energy that it uses. If a country is very poor, very backward, then electricity is a small component of the total energy. People use coal, petrol, kerosene, light and kerosene lamp and all. As they're becoming more advanced like US or Germany and all, then everything becomes more electricity. Everything becomes more electricity. When you're cooking, your gas cooking stove doesn't become LPG, it becomes electricity. Okay? Air condition, everything electricity. So electricity conversion is happening more and more frequent everywhere. And transistors are also at the heart of electricity. And transistors also, they are in transceiver and receiver, transmitter and receiver of a cell phone, of a radar, a satellite. These are not microprocessors, these are not logic gates. These are connected to the antenna in a way, you can say, to send the signals, the electromagnetic signals that are actually bringing towards the Instagram photo or the Facebook video. Those are coming in the form of electromagnetic waves. And those are also processed, received and transmitted by transceiver, transistors in a circuit, okay, in an amplifier. So there are many uses of transistor. Transistors are also memory devices. Now you see, in olden times, not actually olden times, even now, this magnetic hard drive, that was not transistor based. This magnetic hard drive was the memory drive that we used to call it magnetic drive. The hard drive, laptop or a computer was actually magnetic drive. Now recently, when I say recently, few years, in 10 years maybe, the advancement in transistor based memory is so fast, we call it flash drive or solid state drive. It is very simple. It's a flash drive for a solid state drive SSD, and this can have much more density. This can have much more data storage. It is super fast. So nowadays, if you actually buy a laptop, you can actually buy a laptop with solid state drive memory. And if you buy that laptop, and you can see the cost actually. Cost is coming down. In another 5 years, it will actually become much cheaper. It's so fast. The RAM is so fast, you can boot up the computer very quickly. Okay? So that is because a transistor type architecture is enabling the memory storage. Okay, this magnetic hard drive memory is still there, but it is slowly going away now. See how technology changes. Is this CD and DVD? These CDs and DVDs did not exist when I was a small kid, when I was in school. This came when I was in college, and this became extinct when I became a professor, when I started doing a job. See, a technology came in my lifetime, and a technology died in my lifetime. Okay, in another 10 years, for my child, for my baby, when he grows up, if I show him this picture of DVD and CD, he will have no idea what these are. Okay, he will have no idea what these are. So you see, technology is changing so fast. In our own lifetime, we can see technology coming and dying. Isn't that amazing? Again, transistor is the heart of many of these things. Okay, so CD and DVD doesn't have transistor. This just went extinct. Okay, because of many reasons. So the plot here shows how many terabytes can you store in 1 by 1 inch area. This line shows solid state drive device technology, and this line shows magnetic technology. You see, initially magnetic technology was higher until 2014 or 15, but now in the last few years, magnetic drive compared to magnetic drive, semiconductor based technology is going very fast in terms of memory storage. So that is another use of transistor. Okay? Now there are many transistors other than silicon. By the way, silicon is not the only transistor in the world. Sorry, not the only semiconductor in the world. You can make transistors for other semiconductors also. So this is a periodic table, one part of the periodic table, and all of you know periodic table very well. I don't need to explain. So you can make different kind of semiconductor. Okay, for example, you take group 5, boron, aluminum, gallium, indium. You take group, that is group 3, group 5, nitrogen, phosphorus, arsenic, antimony. You mix them. Okay, and you cannot randomly mix them, by the way. There are many rules there. Excuse me. You have aluminum, gallium, indium, phosphide or arsenide. For example, aluminum phosphide, gallium arsenide, indium phosphide. That's one family of semiconductor. Then nitride, aluminum nitride, gallium nitride. That's another family. Antimonide is another family. Or you mix group 2, zinc, cadmium, mercury, with group 6, oxygen, sulfur. So you have zinc oxide, you have cadmium telluride, mercury telluride. So these are semiconductors. These are different semiconductors, not silicon. And they have their own applications, their own properties. Their properties are very different from that of silicon. And they are useful in different applications where silicon cannot do the job. For example, silicon cannot emit light. Because silicon cannot emit light, you cannot make LEDs or laser diodes with silicon. Right? So that is a different kind of material. Right? So for example, silicon carbide is used in power switching, power electronics. Aluminum, gallium, indium, phosphide, and arsenide is used in visible, near IR, infrared, red, and even yellow type LEDs, detectors, solar cells. Indium gallium nitride is used in blue LEDs, high power transistors, UV LEDs, and so on. And antimonides are used in mid-infrared detectors. Okay, zinc oxide, cadmium telluride, they are used in also mid-infrared detectors. So gallium nitride, I will talk about a little bit because this is a material that I do research on, so I have to advertise or sell this material. The gallium nitride is a semiconductor which is used across the streets, across our garages, our homes. Do you know why? How? Gallium nitride is the second most widely used semiconductor after silicon. Can anyone tell me where is it used across the street, in our garages, in our home? Can anyone tell me? Where is the gallium nitride? Right now, probably you can see a gallium nitride device. Right. It is used in your LED bulbs. All the LED bulbs that you buy, whatever, those LED bulbs actually have gallium nitride that emits the light. Okay. So an LED is not a transistor, of course. LED is just remember that I'm just giving an example. An LED actually has two types of layers. One is called a P-type layer, one is called N-type layer. So let's not go about the details of that. When you apply voltage, there are two types of carriers, electrons and holes, that recombine and they emit light. Okay. So the LEDs that we have actually emit blue light. And inside the bulb, there is something called a phosphor coating that converts the blue light into white by mixing with some yellow component. That's why the light, the bulb that you have, is white. If you carefully look into LED bulb, you will see that there is a slight bluish tinge. That is because the LED is actually blue. You are converting the light to white. For making this LED, which is based on a semiconductor called gentleman from Japan, got the Nobel Prize in 2014. Okay, by inventing this blue LED that made our white LED possible. And you can see that LED is now everywhere. This is a road, highway. You see these lights, bluish tinge lights, they're all LED. I don't have to tell you about the use of LED, you know it all, right? So this is another semiconductor. The same semiconductor, gallium nitride, is also very useful for power switching of power electronics. So this is a slide, again, let's not go into the technical details. This is an indigenously built gallium nitride power transistor that we have done at IISc with my colleagues and students. These are packaged devices. This is a wafer on which gallium nitride devices are fabricated. This is for carrying 5 amperes of current. This kind of devices will be very helpful in future in charging vehicles or other kind of. Okay. This is to show that at IISc also we are doing a lot of research in this area. Okay, I think relevant. Someone wants to ask a question.